banquet. Okay, so our last speaker, please come up. Oh yes, Professor Shizhen Zhao. Professor Zhao is a tenured associate professor at Shanghai Jiao Tong University. He got PhD from Purdue University and worked in Google for several years. And so his main research focus is on hybrid optical data center networks for AI workload. Okay, and today he will be sharing us his recent work on the design of a high-performance routing protocol in AI clusters. Okay, let's welcome.
So thanks for the invitation from Professor Chen. Okay, so what happens? Okay, 这个。Okay. So hello everyone. My name is Shizhen from Shanghai Jiao Tong University. Today I will talk about the routing design in AI clusters. Okay. So currently the AI traffic is growing pretty fast. Starting from 2017, so we can see that the AI model size has increases by more than 10 times. And the computation capability also increases very fast. But unfortunately, the network bandwidth increases much slower. So this means that if we stick to the original network design principle, actually we view network as a black box. So then network will quickly become a bottleneck for AI. So one way to solve this problem is to build a domain-specific network. So for example, for AI. So actually for AI tasks, so the underlying communication mainly comes from collective communications. So for example, this all-to-all communication, all reduce, all gather, reduce, scatter, and so on and so forth. And these collective communication patterns, they have different traffic patterns, but they share some common features. So for example, this AI traffic pattern, many times they are predictable. For example, for the ring or reduce, it's just the communication pattern is a ring or multiple rings. Okay, but sometimes this traffic pattern also exhibit some uncertainty. For example, the all-to-all V communication pattern. In large language model, we have the attention layer. We have MOE, expert, parallel. So between the attention layer and the MOE, so there is an all-to-all V communication pattern. So because the horsepower of the experts can change, so therefore the all-to-all V pattern may not be that regular. And the second characteristic is that because it is collective communication, so actually many flows start at the same time. And they may the traffic may burst at the same time. And it is delay sensitive because the tail latency matters, because we have to wait for the last flow to finish before we can do the computation. And another property is that AI workloads has low entropy, meaning that so the many flows are large flows, but the number of flows are small. So therefore, if you just do ECMP, it's very difficult to balance the traffic in the network. Okay, so based on these features, we need to do design a network. Okay, so this picture I show that the big picture of my research. So actually, I focused on building hybrid optical and electrical networks for AI. So which requires a cross-layer optimization for topology, routing, transport layer protocol, and collective communication. So in today's talk, I'm not going to talk about everything. So we just focus on routing and the load balancing, so which correspond to 2 of our SIGCOMM papers. Okay. So I will first talk about load balancing. Okay. So for AI workload, because it has low entropy, so people started thinking about doing packet spray or fine-grained load balancing for AI in order to better utilize the network capacity. For example, the UEC, they performs packet level load balancing. So basically, for each flow, it just simply spray the packets among multiple passes. And then at the receiving side, they reorder the packets before delivering to the end hosts. And in China Mobile, they proposed this GSE. GSE has a different granularity when they do load balancing. It performs a packet container level load balancing. Actually, each packet container contains multiple packets. Okay, anyway, so this fine-grained load balancing may cause packet disordering. Okay. So then, based on this packet disordering, we need to think about when we design a routing protocol, what kind of properties we want to achieve. So first, we want to achieve in-order delivery. So with packet reordering in the network, maybe at the end host, we can have a reordering buffer to reorder the packet before delivering to the end hosts. So this is called in-order delivery. And the second property is lossless transmission. If we have a traffic packet lost, we have to retransmit the packet. This will inevitably increase the tail latency. And that's why we need this. The third one is out-of-order capability. I think the first 2 are pretty common. The last one actually describes the capability of using multiple paths, of doing fine-grained load balancing. The higher out-of-order capability, the higher out-of-order packet delivery can be tolerated by the network. Okay. So if we can, so the out-of-order capability allows us to better utilize the network capacity. But initially, we want to design a protocol that achieves all these 3 properties at the same time. But we tried, but we failed to design a protocol that can achieve a high throughput. So then when we take a closer look into this problem, we found that simultaneously achieving these 3 properties may lead to a new type of deadlock, which we call it order lock. We can look at this example. Suppose we have n+1 packets being transmitted in the network. So the packet 1 is transmitted through path 1. All the other packets are transmitted along path 2. But unfortunately, packet 1 arrives later. And in this case, suppose that the packet 2 and up to packet n has arrived at the reordering buffer. Because we don't want to lose packet, if packet n+1 goes into this reordering buffer first, then so the receiver buffer cannot reorder the packet because the packet hadn't arrived. And because it cannot drop packet, so packet 1 cannot arrive at the destination reordering buffer. So then we see a deadlock. Okay, So actually this we call it order lock. But notice that this order lock is different from existing locks. For example, we have previously we have head of line blocking. So head of line blocking happens when there are two packets. The first packet is going to the first pass, while the second packet is going to the second pass. Because the first pass is full, so the packet 1 blocks the transmission of the second packet. This is called head of line blocking. But eventually, when this pass, the packet transmitted in this pass, eventually it makes room for packet A, and then the system just keeps going. So this head of line blocking only reduces network throughput. It won't cause a deadlock. So another lock is PFC deadlock. So when we have cyclic buffer dependency in this network, so it is possible that there is a PFC deadlock. I won't go into the details. So note that, so for order lock to happen, even if the network does not have cyclic buffer dependency, we can still see order lock happening, as long as we want to achieve all these three properties at the same time. Okay, so clearly order lock is different. Okay, then we want to rigorously define what is order lock, what is the out of order capability in order lock. Okay, so for out of order capability, we want to at the source of a network, we have a sequence of packets transmitted. And then on the receiver side, these packets may arrive in a different order. So for each packet, we can count the number of packets that arrives, that has larger index, but arrives earlier than this packet. So this means, okay, the out of order level of a packet captures the buffer requirement that is required before receiving this packet. And then we can calculate the maximum out of order level for this sequence. Actually, this maximum out of order level characterizes the reordering buffer requirement. Okay, so we say that a network protocol is O, has the out of order capability. It means that, okay, there exists a packet arrival sequence, a possible arrival sequence, P prime, and such that the maximum out of order arrival level is greater than or equal to the receiver's reordering limit. Okay. So this is what we call O. Okay. So then we look at how severe is order lock. So we do some experiments to see the frequency of order lock. So here we test the three O policies. First is random packet spree. The second one is QDAPS. QDAPS choose an outgoing port with slightly higher Q length to minimize the out of order level of the sequence. But unfortunately, it still leads to a pretty high out of order level. The third approach is adaptive routing. So we always choose send the packet to the port with the least Q length. So here, this is the topology we use for simulation. So we can see that for all these three policies, eventually the per sending rate drops to 0. And so this means auto lock happens. Okay. We also try, this is just a one flow experiment. We also try sending many flows in this network. So these numbers characterize the possibility of encountering auto lock. Okay. So actually, auto lock happens pretty frequently. Okay. So then we think about, can we increase the reordering buffer to avoid this O? But unfortunately, with packet spree and the PFC, the on-the-fly packets of a flow can be far more than the bandwidth delay product. So think about if there's no packet spree, okay, the maximum number of packets on the fly is bounded by the bandwidth delay product. So therefore, the maximum out-of-order level is bounded by this BDP. But with packet spree and PFC pausing, for example, here, suppose that the packet with index 1 is on this slow path, and this path got a PFC pause. Okay, and then the maximum order level would increase, would be pretty large. So here we also did a testbed experiment. So we just send multiple flows and count the maximum order level. So as you can see that as we increase the flow size, we can see that the maximum out-of-order level also increases. Actually, it can be multiple times of the bandwidth delay product. Okay. So this means that if you want to do packet spree, so your policy must be O. Okay. Okay, therefore, so this means that when we design a protocol, we shouldn't design a order log risky protocol. Actually, when we look back into all the routing protocols in the past, we found that they don't know about auto lock, but they try to avoid auto lock when we design their protocols. So this means we can, based on these three properties, we can classify the existing routing protocols into different categories. For example, this one is you drop L. L means lossless. So you drop the lossless requirement. So this you get lossy RDMA. And for example here, you drop I and L. I is in-order delivery lossless. O is you drop O. You drop O. This means that you maybe you don't do packet spree. ECMP belongs to this category. And another interesting thing is this LO. In the network, you want the network to be lossless, and you also want packet spree, but you drop I in order delivery, meaning that you don't do the reordering at the receiver side. You just leave the reordering to the application. Okay. So we actually simulate 6 different protocols. For this LO, actually is the SRNIC from Professor Chen. I think it belongs to LO. We try different collective communication traffic patterns. So our observation is that this LO achieves the best performance among all the simulations. Okay. So next, I want to talk about the routing. Okay. So based on our previous discussion, so we still want the O policies because our O offers you the best performance. So all policies meaning that we need to perform fine-grained load balancing among multiple passes. But how to split the traffic among multiple passes? So here, one strategy is to, optimized strategy is to traffic engineer. So basically, given a traffic matrix, you will compute how many, what the fraction of traffic that should be split among different passes. Okay, can you do this? But what's the challenge of doing traffic engineer? Okay. So one of the big the main challenge in traffic engineer is to handle traffic uncertainty. But in a network, traffic pattern changes all the time. So if you count the microsecond burst, you will find the traffic pattern can change at the microsecond level. But apparently, it is impossible to change the TE configurations every microsecond. So actually, for example, in Google's deployment, Google deploys traffic engineer in their data center. They only do traffic engineer every tens of minutes, hour level, at the hour level. Okay, so this means that your traffic engineer should be able to tolerate these traffic bursts. Okay, here we use an example in this figure. Initially, for example, we can get a traffic pattern based on historical traffic matrix, and then we compute a TE solution, and then we use this TE solution for the next traffic pattern. So we can see there are many high bursts, high spikes. This means that the traffic burst hurts the performance of traffic engineer. And Google actually does something in their data center. It calls hedging. I will talk about the idea of hedging in the next slide. In this slide, okay. So think about the traffic engineering solution. For example, we have a traffic demand from this source to this destination. So one routing solution would be we send all the traffic from this node to this node. So maybe this traffic, the total amount of the traffic is small. Maybe this direct link hop has enough capacity to handle this traffic. But I will say that this approach is prone to traffic bursts, because when traffic bursts, all the bursts need to be handled by this one link. Okay. So another approach is that maybe we can sacrifice some efficiency of the traffic engineering solution. We can split the traffic among these three passes. Okay. Because it uses two hop passes, the efficiency reduces, but the robustness increases, because when traffic bursts, so the traffic burst will evenly spread among all the three passes. This is a key idea of hedging. Okay. But in our work, so our observation is that the burstiness of different traffic source destination pairs actually varies. Here we just use several traces. The first one is from a wide area network. The second, the third one are from Facebook's data center traces. So here these numbers are the normalized variance of the traffic. Okay, we can see that they have different numbers. Okay. So if we just treat different source destination pairs equally to guard against the traffic burst, it would definitely hurt the performance. So here is our key idea. We want to treat the different source destination pairs differently based on their likelihood of traffic burst. So for example, we suppose that the predicted traffic pattern is 222. And then if we don't do any optimization on the traffic burst, the TE solution would be this one. So the splitting ratio are always 1. So then, so let's say in the real case, the traffic from B to C may burst. So we can see that this first strategy, when the traffic bursts, it will the maximum link utilization, meaning that the worst case congestion would be very poor. So, but then if we use a different strategy, so for example, we know that the traffic from B to C is highly bursty, but traffic from A to B and A to C are not bursty. So then we can split the traffic from B to C among 2 passes. And then this strategy 3 offers the best performance, both in the normal case and the traffic burst case. Okay, based on this idea, we can slightly change the formulation of the original TE problem. So originally, this Wij means that the from source I to destination J, so we have K passes, and this Wij is the routing weights along the K's path. So clearly, this number sum to 1. And if the objective is to minimize the maximum congestion among all the links. Okay, so this is the original TE formulation. If we do nothing about it, so eventually the solution, we can see that many Wij would be 1. So this means that whenever the traffic bursts, this Wij may cause severe congestion. And then we only need to slightly modify this formulation, the objective function. So basically the idea is like this. So suppose Dij is a predicted traffic demand. Delta Ig is the traffic burst. So we can compute this delta Ij multiplied by Wij divided by the capacity of this link L. So this is the utilization of the edge affected by the traffic burst. So notice that we have this multiplication term, product term. So in this a new formulation, we just multiply this variance of the traffic demand and the maximum routing weights for each flow. So by minimizing this, we can achieve that. So if this flow is highly bursty, the maximum value would decrease. Okay. So actually, just by changing this formulation, we can get better robustness for this traffic engineering problem. But here, wait. So here we have another problem. So the computational complexity of this burst-aware traffic engineer is pretty high. So next, we study how to reduce the complexity of this TE problem. Okay, so here we thank to the deep learning. We just use a very simple deep learning, a very simple neural network. The input is a traffic matrix. The output is just the routing weights. We just allow the neural network to learn the solution. So we set the loss function as the objective of this formulation. The objective of this formulation. Just by this learning approach, we can significantly accelerate the solver running time. And with this approach, we compare our solution with Google's traffic engineering solution. So we can see that the max link utilization, meaning that the worst case congestion level decreases, and also the flow completion time also decreases. So here we just give a brief explanation that why our approach works. So here we plot on the x-axis plot the variance of a traffic demand, meaning a source destination pair. So the y-axis plots the Wij, the Wij value. So we can see that with Google's approach, regardless of the traffic demand, the variance of traffic demand, so the routing rates is uniformly spread in this range. But with our approach, as the variance of traffic demand increases, the maximum Wij decreases. Okay. So this is the last slide of my talk. So here, based on actually, I think that this AI for traffic engineer has very many promising research directions. So for example, in tomorrow's talk, we have AI approach to handle network failures. So basically, we want to solve the TE problem to guard against link failures or node failures. And the traditional approach is they use integer programming to solve the problem. The computational complexity is extremely high. But when we use our approach, the traffic AI approach, so we can significantly reduce the computational complexity. The second one is handling network dynamics. So one way of using AI for routing is that when the network changes or when the traffic demand pattern changes, you may think that maybe we have to retrain the network. So that would be very costly. So here we use another idea that to solve this problem. So think about, so when we solve a traffic engineering problem, it's basically a linear programming problem. A linear programming problem, you can solve it by the primordial gradient descent algorithm. So is the gradient descent, the primordial gradient descent algorithm, it does not care what kind of topology you are talking about. It does not care the traffic pattern. It can be always used. So then we think that maybe instead of learning the solution from end to end, we can learn the gradient descent is an iteration process. So this iteration process can be used for arbitrary topology. So if we can learn this iteration process, then our approach should be adapt to many different situations. Okay, so actually this way we have already have some preliminary results, and we put it in on the archive. Okay, so here the third one is a joint optimization of collective communication and routing. So actually, if you look at this part, we have already seen there are many papers jointly optimizing traffic engineer and collective communication libraries. But a common problem is that the computational complexity is extremely high. At most, they can support maybe 20 GPUs. So if it is larger, it can also give a solution. So then we think about maybe the AI approach can be used here to get much better scalability. So the last one is a closed loop traffic matrix prediction for TE. So usually when we do a TE, we believe that, oh, maybe we need a traffic matrix. But how to get a traffic matrix? We think, oh, maybe we can predict a traffic matrix. But the prediction is inaccurate. So maybe the prediction, but if when we do this traffic engineer, maybe some demand, even if you predict very accurately, maybe it is not, it won't help to improve the traffic engineering performance. So some traffic demand, maybe we should predict it more accurately. So the traffic matrix prediction and the TE algorithm, there is no feedback between these two. So here we want to do maybe we can do a closed loop traffic matrix prediction and for the TE, and maybe we can get better performance. Okay, this concludes my talk.
Okay. A very informative talk. Okay. So the PC chair is very hurry for banquet. We have one question. Okay.
Thanks for your great talk, Professor Zhao. I'm wondering. I have a quick question. If we add the window boundary in the center, will the order lock avoid? Can the order lock be avoided?
You add a
Add
window.
the window boundary like what IRN did. They just limit the in-flight bytes.
Okay,
Yeah.
I see your point. So actually, if you add maybe you have some credit-based end-to-end credit-based flow control. You want to limit the in-flight packets, but that will reduce the throughput of this network. And also, when you limit the in-flight packets, basically you reduce the maximum out of order level. So this means your policy is no longer an O policy. So for example, if the maximum in-flight packet is 10, then the MOA is at most 10. And then if the 10 is smaller than the reordering limit, then it's no longer an O policy. So it does not violate our result.
Okay.
And also limiting this in-flight packets will significantly reduce network throughput.
Right. If you allow direct packet placement, right, without requiring reordering in the NIC, will that mitigate the problem?
So you mean directed packet placement?
In the buffer, in the host, do not need to wait
Right. If you directly, if you skip the reordering process on the buffer, on the NIC, and you
will
directly
that solve the problem?
that will solve the problem, but
Okay.
that's not. But you actually relax the in-order delivery, the I. You
Right, I know.
relax I.
Okay. Right.
Okay, thank you.
Okay, let's thank the speaker again. Okay, yes. Yeah, we have more questions tomorrow panel. So local chairs lead us to the banquet. Okay, local chair. How? Yeah, we need to go. Right.
So actually, so actually,
lead us to the.
Yeah, so we will have some bars just downstairs. You go to, we just go downstairs and you look at the volunteers, and we will have bars just in front of this hotel. Okay, so we have 4 buses together. One of them has already left, so the rest 3 will wait for you. So please just move to the bus. Thank you.